ask me if you have any questions, stop me. You're more than welcome to stop me, okay? So in this case, we have 11.41. We have a heat pump that's operating on the ideal vapor cycle with 134A as the refrigerant. And this heat pump is being used to heat water from 15 to 45 Celsius at a rate of 0.12 kilograms per second. Now before I read further, check it out. This is a heat pump that's being used to heat water from 15 to 45. So what are we trying to extract from this guy? Are we trying to extract the QH that comes out on the top? Or are we interested in the QL? What is this heat pump used for? To give QH to something or to extract QL from somewhere? Not a rhetorical question.
We're trying to give to the water, right?
Yes. So, what's the conclusion?
It'd be the QL into the water, yeah?
So, watch out. Okay, this question is especially important for all this week and all these problems because it's a simple thing, but it gets a lot of students, okay? This is the normal, let's say the normal refrigeration cycle. Here we're giving work to the system. Over here we're extracting some energy. Over here we're giving out some energy, right? That's what the QH and QL is. Now, if you have a fridge and you want to keep the inside of the fridge cold, the inside of the fridge is going to be over here, right? This green part's my inside of the fridge. So whenever this guy extracts heat and then goes and releases the heat outside, I'm maintaining that guy cold, right? But in this case, I have a heat pump, so I want to heat up water. If I take energy away from the water, so if I do this, there's no way my water is going to go from 15 to 45, right? It's just going to go cooler, not hotter. So this is not what I'm interested in. So this is not working as a refrigerator, it's working as a heat pump. I'm interested in this. So this guy is giving energy to the water, that QH. It's leaving the cycle and going to the water. It's precisely the idea. And the reason why I'm stopping as in doing this is because everything in relationship to this problem is going to be related to QH, not QL. So if they were to ask what's the load, the load of heat that this guy is outputting, it will be QH, not QL. This is something that's not going to be said. You guys have to know. If we're after the coefficient of performance of this guy, remember coefficient of performance is the desired output over the required input. In this case here, the desired output can be QL or QH depending on what you're using it for, right? So the coefficient of performance will change according to what you have. In this case, we want QH. It's going to be QH over the work of the pump that we're putting in there. So we need to make sure that we know what this guy is doing, whether it's working as something that's removing heat from a place or something that's giving out heat to increase the temperature of something or to make our place more cozy, more warmer, anything like that. Okay, so with that said, that's the one thing you guys need to watch out for. And the next thing is over here. Check it out. Check this out. Ideal vapor cycle. Ideal vapor compression cycle. With that is said, if it's an ideal, you guys want to write this down. If it's an ideal cycle, there's a couple of things that we know that will happen. First up, when we go from state 1 to state 2, we know there's no creation of entropy, right? It's a completely reversible change in state, right? So this guy shoots straight up here from 1 to 2. The other thing that we know is that the dome hits 1, so state 1 is a saturated vapor. And we know that state 3 is a saturated liquid. So these things are things that I need to know prior to solving this question, or else I'm not going to be able to solve it. Okay, so if I'm redrawing this this guy here.
Just had a question, Pablo.
Go.
Does that mean all entropy can be assumed to be 0 for this question, since it's
No,
an ideal? Or would you have a value and you'll use the same value, like as if it was a reversible state?
neither.
Oh,
Entropy is not 0, right? Entropy is a measurement of, you can think of a disorder or how concentrated energy is, but it's not going to be 0 ever, right? The delta S is 0. In other words, when I go, whatever the entropy is on 1, it's going to be the same on 2. I'm not creating more entropy going from 1 to 2.
yeah.
Different, very different thing. The other thing is that we have isentropic going from 1 to 2 and from 3 to 4. But not from 3 to 4 because it's a throttling process. But from 1 to 2 is going to be isentropic. But from 2 to 3, and you can see on the S here on this graph, from 2 to 3 it changes, right?
Yeah.
Going from states with lower disorder. And we go from 3 to 4, the entropy on them is the same on the throttling process. The entropy is the same, but we do create some entropy. If you think about it, on the throttling process, what's happening is we have a high pressure fluid going through a very small tube. That's the simplest throttling process you can have. So through a capillary tube. So what happens in there is that you have a high pressure guy going into a low pressure state. There's no way that on its own, this low pressure state is going to go back that capillary tube and into the high pressure state. You need to put energy to have that happen. So it's not reversible, right? We can't have that being a reversible process.
Yeah, thank you.
So on an ideal cycle, what we know is that 1 to 2, it's going to be isentropic, no creation of entropy. So watch out, it's different from having entropy equals 0. And state 1 is a saturated vapor, and state 3 is a saturated liquid. So when I'm drawing the dome, I'm drawing that little saturation line. When I'm drawing this, it hits precisely on 3, and then it hit precisely on 1. Okay, that's what's the ideal vapor compression cycle. Now, that's going to be very useful for us to solve this question because we're going to need to define the states as per usual. And to define the states, we're going to use those definitions as one of the things that is going to help us to solve this. Anybody has any other questions before I move on? Okay, so let's define the states like we always do. Why do I not have my, there you go. Okay, so let's start with state 1. Check out, we know 2 things for state 1. From the wording of the problem, we know the pressure. And because it's ideal, we also know it's a saturated vapor. That means that defining the state's pretty easy because we can go straight into table on the pressure table. And let me just make sure I know, I'm giving you the number of the tables because A12. We can go straight into table A12, it's a pressure table, and I can grab H1, which will be equal to H sat vapor, which is 251. I can also grab my entropy 1, which is going to be useful precisely because there's no change in entropy. And check it out, Jason, it's not 0, right? It's 0.93, check this on the table. 2.93026 joules per kilogram Kelvin. So whatever the state 2 is, I don't know, I'm not sure if I know anything from state 2, but I do know that if it's an ideal cycle, then its entropy is going to be also 0.93026 as opposed to 0. So let's take a look in state 2. On the problem, we have the 2 limits on pressure, right? 1.4 megapascals on one end, and we have 0.32 megapascals on the other end. So 1.4 megapascals over here, and S of 2 equals S of 1. So we have 2 properties for it. That's all we need. And what we're going to do is we're going to go do that little dance we always do, go on A12, and you're going to see it's superheated. I'll just do SH. So we go to table A14. And on A13, we can grab H2, and H2 is 282.6. I had to interpolate this to get this value, and I interpolated between, I'll put it here just for your reference.
I have a quick question.
Yeah, let me just put these values in. 276 and 286. So I had to interpolate with these 2 values. Yes, what's up?
What would you do if the entropy value was lower than on the table for the pressure?
It's in a compressed fluid.
Okay, thanks.
Yep. So if the entropy is lower than the liquid, right? That's what you're asking.
Yes. That's it.
Yeah, compressed fluid.
Thank you.
So if it's compressed fluid, we can treat it like we've been treating compressed fluids before. So we can do, can approximate it to the saturated liquid, or we can interpolate if it's still different from the saturated liquid. So from state 3, we also know two things. We know also the pressure, it's 1.4, right? The same pressure as state 2. And do we know anything else about state 3? Yeah, it's a saturated liquid because it's an ideal system. It's a saturated liquid. Saturated liquid. And knowing the pressure, then we can go straight on H12 and we can grab H3, which is equal to H sub liquid. And that will be 127. And for this one, since we're doing the first time, I'll do state 4 as a separate one. For the next ones, I'll just do it together because state 4, so because from 3 to 4, it's a throttling process. Then H3, so my H4 is also going to be 127.25. So because this guy is ideal, right, and only because it's ideal, we have this extra bit of information here. We know this guy because it's ideal. We know this guy because it's ideal. We know this guy because it's ideal. Okay, we know that if we didn't know that, we wouldn't be able to solve this. Now, we're being asked, let me get the question again. We're being asked, what is the power input to the heat pump? Okay, and we know that the heat pump operates between 1 and 2. So if we were to grab the difference in enthalpy from these two guys, we would have the energy that the pump consumes. But since it wants power, we need kilowatts, so we need watts, we need mass flow rate. We don't have the mass flow rate of refrigerant 134. But we can find that out easily, right? Because we know right here, we know that when you go from 2 down to 3, that's when we have the release of energy. And this energy is exactly what's being used by the water to heat up from 15 to 45. Okay, so now we can do a little energy balance over there on our condenser. So let's do that together over here. Let's do a little energy balance. So at the condenser, sum of energies will be 0. So in other words, all the energy that the water absorbs has to be equal to the energy being released by the system. And I can do this either energy or power. In our case, power is more useful, right? So there's two ways you can go about this. And this is what we were talking just before when finding the energy of the water. Okay, there's two ways you can go about it. You can grab enthalpies from the table, H from table, or you can use CP. Why can I use CP if I just learned that CP varies with temperature and all that and all that? Okay, let's have a look. I'll show you guys. Curve 3 here, top of table. Okay, I'm going to go all the way up to table A3. A3, water. And I'm going to be looking at the last column, which is specific heat CP. Okay, I'm looking at this column here. And you'll see the following. Check out how CP varies with temperature, right? At 0, it's 4.22. At 25 is 4.18. At 50 is 4.18. 75 is 4.19. All right, we're going from 15 to 45. So our bulk temperature for this guy is 30, which is going to fall exactly on 418. What if we wanted to know what's the CP at 15? We could interpolate between these two guys. It would be something around 4.19. Right. The vast majority of water is going to be at 418. And note how that's not going to change when we go all the way to 45. Right? It's going to be 418. So because we know these values, all these values, we can approximate it to CP equals 4.18. Now, as a, share this guy again. as a as something you guys can do is you can actually go ahead and test out these two things. Grab the enthalpies from the table, see what's the difference from going from 15 to 45 at the pressure that we have, and check and do it this way too and see the difference that you get in value. I can assure you it's going to be very little. Now in this case here, we can do, if you want the mass flow rate, you may also need to multiply by the mass flow rate of water. Right, so let's actually do the nice way, remove this and just remove the dot for now, and just do down here. Okay, if I want the power that water is absorbing, I can do mass flow rate of water times my CP times my delta T. And in this case here, the mass flow rate of water is 0.12 kilograms per second. The CP can be 0.18. And my delta T is 45 minus 15, so 30. Okay, kilojoules, let's do this quickly. Kilograms per second, kilojoules per kilograms Kelvin. Right, so Kelvin goes away with Kelvin. Kilogram per kilograms, kilojoules per second, kilowatts. So the energy of my water is about 15 kilowatts. Which means my QH, now going back to this guy here, which means my QH, hot has to be about 15 kilowatts. Means that the mass flow rate of refrigerant times the difference from QH, which is when I went from state 2 to state 3. 2 minus 3 has to be equal to 15 kilowatts. Okay, so I can just divide my my 15 by the difference in from 2 to 3, and I can find out what is the mass flow rate for this guy. It ended up being 0.09686 kilograms per second. With this, we can finally, once and for all, find what is the work that is required for my pump, right? Because I know my pump, like we said before, I can find this by doing H2 minus H1, and that's going to be just fine. That's going to give me in kilojoules per kilogram. Or I can do what's the power required, which is just going to be a mass flow rate of the refrigerant going through it times H2 minus H1. Okay, so we can do all of this guy will be 0.09686. 283.6 minus 251.93. About 2.97.